Okay, well, let's continue today with our discussion of acids and bases. Let's seek to finish this up and thus seek to finish up chapter 1. What we're going to do today is look at some predictive ways, or what we call trends, of acids. Last time we learned how to see how strong an acid was by simply looking at its pKa value. But now we want to see if we can predict how strong an acid is just simply looking at it without any pKa values. The first one, or the first way we're going to look at it is by looking at what row the acid is in. Let's look at a couple of examples here. If we look at these three molecules here, these three can act as an acid by giving off a hydrogen or a proton. If we did that, okay, so remember the proton we can symbolize by H+. So let's take off a proton. And by doing so, that will give us a negative charge for its conjugate base. So we get NH2 minus, OH minus, and then F minus. So these are our three conjugate bases from these corresponding acids. And how do we determine which acid is the stronger acid? We do it by looking at these bases, okay? And the rule is the more stable this conjugate base is, the stronger its corresponding acid was. Okay? So what we want to do is figure out which of these three is the more stable base. So what's the difference in each of these? The difference is, well, we have a negative charge, so that's the same, but the difference is this negative charge is on nitrogen, this one's on oxygen, and this one is on fluorine. Well, if you look at the periodic table, the fluorine is the most electronegative. And so this fluorine can thus stabilize that negative charge the most because it's pulling in on it the most. Okay? So here, the rho argument is an electronegativity argument. So this one here will be the most stable. So this acid here, HF, would be the strongest acid. Okay? Then the next strongest acid would be H2O, then the next one would be NH3. If you compare these pKa-wise, HF has a pKa of 3.3, H2O is 16, and ammonia, NH3, is 33. So you see that as we go away from the electronegative atom, it gets to be a weaker acid. Okay? So that's the first argument, the rho argument. Okay? Let's go on to the next argument, which is the group argument. And looking at a group argument, let's look at these acids here. Okay? Here we'll look at HF, HBr, and HCl. we want to see if we can predict which of these would be the strongest acid. Okay? Well, again, we do the same argument. We remove a proton, and we get its corresponding conjugate base. Each of these three here. Okay? Note that each of these are in the same group or in the same column of the periodic table. So here it's a different argument than an electronegativity argument. Okay? Here it's going to be what we call a size argument. Okay? Remember, as we go down the periodic table, if you look at fluorine, chlorine, and bromine, remember the size, you can always think of like Frosty the Snowman. Fluorine, smaller, but as we go down, we get bigger, and bromine even bigger. Okay, so think of Frosty the Snowman. Okay, and the theory is that the bigger the atom is, the better it's able to stabilize that negative charge. It has more volume to stabilize the extra electron. Okay, so it's a volume or a size argument. So this one here, Br minus, would be the most stable, and so HBr would be the strongest acid. Okay, and it is. If you look at the pKa values, HF is 3.3, HCl -7, so pretty strong acid, but HBr gets even better than that at around -8. Okay, so as we go down, we get a stronger acid. Okay, so these are the first two trends that we want to have under our control. The last trend that we'll look at is the hybridization argument. Okay? In the hybridization argument, we haven't studied hybridization yet. We'll be studying it in our next topic in chapter 2. Okay? But let's just sort of get a little picture of this for right now. Okay, and we'll come back and get this under our belt more solid in chapter 2. But here, let's look at these two things acting as potential acids. And again, if we remove a proton, we get the conjugate base. So here you get CH3 minus. And if we remove one of these hydrogens, we would get this conjugate base here. Okay? Well, this conjugate base, this carbon is an sp3 carbon. And this carbon here is what we call an sp carbon. Okay? If you look at the two, and we want to ask ourselves, which one here has more S contribution to it? Okay? Here, this is, if you count the S and 3 P's, we have a total of 4. Okay? 1 S and 3 P's. So the amount that this is S would be 1 out of 4 S character. Over here for the SP, we have what? 1 and 1 for 2. And so here we have 1 S out of 2 of these letters. So we have 1/2 S character. Okay? And the theory is that the more S character it is, the more it can stabilize this. Okay, so that's our theory for hybridization. The more S character we have, the more stable the conjugate base can be. Okay? And again, we'll get into what this stuff means, sp3 and sp, in a little bit. But this is what you want to take away. So this conjugate base would be more stable, and so this one here would be the stronger acid. Okay. So these are the three trends of acids that you want to remember in order to predict which acid is the strongest. Okay. So this here completes chapter 1. And what we'll do now is move on into chapter 2. Again, make sure that you're reading this stuff in the book so as to make it more solid in your minds. Just coming to lecture and here it's not enough. Reading it always causes it to sink in more. So read, lecture notes, and then tackle that homework immediately. Okay, well, let's now migrate over to chapter 2. In chapter 2, we have a variety of topics that will be some review, but some we will get into more of organic chemistry. Okay? The biggest part of chapter 2 has to deal with what we were getting into, the hybridization theory. And that's what we want to go ahead and tackle first, since it's kind of on our mind. And this topic here we will call molecular orbital theory. Sometimes abbreviated MO theory. Okay? And here what we're going to do in this very long topic of chapter 2 is look at the nature of bonds. Okay? You know, for example, we saw the Lewis structure of water to be something like this. Okay? And so we see that we have two bonds in here. Well, what molecular orbital theory is going to do is look at the nature of those bonds. What exactly is going on in those bonds? Okay? What is the functionality of the bonds? Okay? How can we give those bonds more description, more analysis? Okay? So that's what we want to get into with this theory here. Okay? So to do so, what we're going to look at are two different kinds of bonds. The first kind of bond is what we call the sigma bond, or the Greek letter sigma, the small s in Greek is the sigma bond. A sigma bond is what we call a head-on overlap of atomic orbitals. A head-on overlap of atomic orbitals. Okay? The second kind of bond is what's called a pi bond that we'll be talking about a lot. A pi bond, what it is it's a sideways overlap of two p orbitals. Okay? So these are the two bonds that we want to study in a little bit of detail here. Okay? Let's come back to the sigma bond. You notice the word atomic orbitals. Okay? Atomic orbitals, or sometimes we'll simply call these AOs. Okay? What were the atomic orbitals? The atomic orbitals were the S, the P, the D, and so on. Okay? Remember, those were represented by the quantum L numbers, okay, back in quantum chemistry. So these atomic orbitals, okay, remember for the S atomic orbital, it was spherical, so we could draw it like that, okay? The P atomic orbital was this dumbbell shape, okay? And the D, we're going to leave the D alone because it gets into very complicated shapes, okay? So all you have to do is remember the S is a sphere and the P is this simple dumbbell shape, okay? We're going to use only those two, but we're going to produce a lot from those two in this molecular orbital theory, okay? So let's study, for example, what would a sigma bond might be. Okay, here it's a head-on overlap. Well, let's suppose that we had two s orbitals. Okay, and remember when we draw these s orbitals that there is one electron that's swimming inside of these orbitals, so let's just draw it by a dot. Okay? Well, when these two atomic orbitals get close enough together, they can then overlap, and in the overlap region, the two electrons are shared. Okay? And so where those two electrons are shared, remember that is a bond. Okay? So here, this overlap would represent this bond, which we call a sigma bond. Okay? So it's just a head-on overlap of these atomic orbitals. Okay? We'll be looking at some more sigma bonds later on as we get into this molecular orbital theory in more detail. Let's go on to the second one. What is a pi bond? A sideways overlap of two p orbitals. Okay, so here are two p orbitals, and there's one electron in each of these. Let's bring them close together. As you can see, I got to bring them real close together to get this sideways overlap. Okay? And so we have overlap here and overlap in the bottom. So you might ask, how many pi bonds do we have? Well, by definition, we only have one pi bond. But you say, I got two shades here, two overlaps. Yes. The way we view that is that here, this is counted as half of a pi bond, and this down here is another half of a pi bond. And so what's a half and a half is one, okay? So the pi bond The way to view it, write it down, is that it's evenly distributed on the top and the bottom of this overlap, okay? So this is one pi bond, okay? So keep that in mind as we get into molecular orbital theory of what a pi bond is, okay? All right, well, let's get into this molecular orbital theory in a little bit more detail now, since we know the two different kinds of bonds. Okay, and what we're going to get into now is the topic of hybridization. Okay? You may or may not have covered it in general chemistry. That's okay. Here we're going to master it. Okay? We're going to look at it very simplistically, and then we'll understand it in a more complex manner. Hybridization. What does hybridization mean? Okay, you've studied hybrids, haven't you, in biology? Okay, a hybridization or hybrids is just simply a mixture of two or more things, isn't it? Okay, so you can think of hybrids from everyday example. Okay, you can think of mixing salt and water, and what do? You get salt water, don't you? Where it has the properties of salt and it has the properties of water. Okay, we mix metals every day to get a new alloy of a different type. Bronze is a hybrid of two different metals, okay, and so on. Are you a hybrid? Yes, we are hybrids, what? Of our parents and their parents and many generations. So we are mixtures of different people to certain extents, okay? But here, in bringing this back to organic chemistry, we're not going to be mixing people in here. We're not going to be mixing metals in here. Instead, what we're going to do is that we're going to mix atomic orbitals, okay? We want to mix atomic orbitals. And the mixing of atomic orbitals that we're going to do are these two here. We're going to mix s and p orbitals to get a new hybridized orbital, okay? And that's what we want to go ahead and try to tackle here, okay? So, since the main atom in organic chemistry is carbon, let's look at the carbon atom in doing this thing. Okay? If you look at carbon, okay, it has a total of 6 electrons. Okay? And so what is its electron configuration setup? Okay. So here is the electron configuration of carbon, 1s2, 2s2, 2p2. Okay? And this is what's called the ground state. Okay? But if you remember when we drew carbon's Lewis dot symbol, it had 4 single valence electrons. Okay? If you look at the setup for carbon here, here are the valence electrons again, and here are the 4, but note that 2 of them are paired. Okay? What Linus Pauling proposed was that one of these electrons gets promoted up so that now carbon can have 4 single valence electrons that we can put around there. Okay? So here are the valence electrons for carbon. Okay? But Linus Pauling then saw another problem, maybe you see it, is that these 3 electrons are of the same energy, but this electron is of a different energy. It's a 2s. So I need to somehow make them all equal. And the way we make this all equal is by hybridizing them. But before we do that, this state here, where we have promoted a lower level electron to a higher energy state, this is what's called the excited state for carbon. The excited state. Okay? And what carbon does is that it's going to hybridize in the excited state, and it's going to form bonds in the excited state. Okay? No need to ask where did the energy come from to move it up to here. Okay? It just simply, this is how carbon exists whenever it forms bonds. Okay? So we'll just leave that alone as that is there. So how do I get these 4 electrons to be all of the same energy? The way we do that is we mix these 4. Okay? So if we mix these 4, to get them all to be equal, what am I doing? I'm mixing a 2s plus 3 2p's. Okay? So I'm mixing an s and 3 p's. When I do that, I get an sp3. Okay? So an sp3 is simply the result of mixing 1s and 3 p's. Okay? I put the 3 as an exponent to indicate I've mixed those 3 p's. And so I have 1 electron in each of those slots. Okay? So these here are the atomic orbitals that carbon will bond in. Okay? And these are what? Hybridized atomic orbitals. Okay? What are the hybridized atomic orbitals? The 4 sp3s. Okay? So let's look at those in a little more detail. Okay? Again, I know this is probably new for you, but just hang on. It'll make sense in the end. So what I have mixed is 1s and 3 of these p's. Okay? So what will that look like shape-wise? Well, I can envision this 1s mixing with 1 lobe of the p. And so I get a fat end on one side and a skinny end on the other side. Okay? And end up getting 4 of these. Okay? So this here is the sp3 shape. So we're going to get 4 of these on the carbon atom. Okay? And what we're going to do is just focus on this fat part here, because this is the part that will do the bonding on the carbon atom. Okay? So let's draw those 4 on the carbon atom. What we're going to do is put the carbon in a box, because we want to put these four lobes as far apart from each other as possible. And the best way to do that is to put them on opposite corners of the box. And they all have their single electron in there. Okay? So these are the four sp3s on the carbon atom in different corners of the box. Okay? You can see it's developing a shape. If you remember from general chemistry, this shape is what's called tetrahedral. Okay? So carbon, when it's hybridized as sp3, has these 4 points in a box, and the shape of that particular carbon atom of an sp3 is tetrahedral. Well, let's make a full molecule by adding a hydrogen atom. Remember, hydrogen is a 1s1 atom. And remember, the shape is spherical. So we'll draw hydrogen as the sphere with one electron. And let's form some sigma bonds here. So we'll overlap here, and here, and here, and here. Okay? So we got these head-on overlaps. So we have 4 sigma bonds of what? An S and sp3. The S coming from the hydrogen, sp3 coming from the carbon. Okay? So this overlap here is my sigma bond. Okay? And I have 4 of those. Okay? Okay? So, what we have done here is we have drawn CH4 in a little bit more detail than what we were used to. Okay? CH4, if you were to draw the simple Lewis structure, we were used to just simply seeing it like this, right? But now, according to molecular orbital theory, I know more detail about each of those 4 bonds. That it's what? These are each a sigma bond of an overlap from an S, from the hydrogen, and sp3 from the carbon. Okay? So we've characterized each of those bonds in more detail. Okay? So we say the hybridization of this carbon is sp3, and so the shape will be tetrahedral according to how we drew it over here. Okay? And what we'll do next time as we bring this to a close is show you a way to draw this shape without drawing the box. We'll introduce a new type of bond configuration to show that, and also have a 3-dimensional molecule to show this shape as well. So let's go ahead and close here for today.